General polynomial patterns. In the last video, we used an abstract number triangle to define a signature to classify quadratic patterns using A, B, and Q. In this video, we'll explore different ways to represent a general signature and select the best one. I'll be following the evolution of my thinking instead of just stating my current understanding. To formulate a general signature, let's explore the example of a cubic equation. Let's see if we see anything interesting. For the cubic, we'll use A, B, C, and Q. Can you spot the pattern? When I first went through this exercise, I also wrote out the 4th and 5th degree abstract triangles to be sure. The answer is that the bottom row is an extract from the Pascal triangle. Not the conventional Pascal triangle, but a polarized version where some diagonal columns are negative values. We can put this into a matrix where the columns represent functions we can interpolate to any index. This allows us to extend our linear system to account for any index in our data. Furthermore, by extending the algorithm from the previous video to take advantage of this fact, we can scan for all polynomial patterns of any degree. Let's take a look at the functions generated by interpolating the matrix columns. There are some rich patterns here, viewing all the functions together vertically, column by column. The first column alternates signs between positive and -1. Next, it seems to increment while still alternating signs. The pattern here is that each column gets 1 degree more complex than the previous. In this case, the odd connection between these functions actually indicates there is a simpler matrix we can use. I know this only because I've analyzed these related functions further and found out they were suboptimal. Let's take a step back. How did this all get started? When we first calculated the quadratic signature, we did so in terms of A, B, and Q, where A and B were the first 2 points of our data column and Q was the quadratic component. Let's revisit this decision. Did we need to use Q at all? What if we just used points in the main column? Okay, so this would work, but what else can we try? Let's try this. In this slide, we place all of our variables at the top of the triangle. And look what happens. The equations at the base of the triangle are precisely rows of the Pascal triangle, without any polarization. By polarization, I mean positive and negative columns. So if we end up using this method to create our matrix, we'll no longer need the polarized Pascal triangle. This is what our signature matrix looks like when we use the top of the number triangle for our variables and the base for the equations. It has similar properties to the table of equations we looked at earlier. Each progressive column increases in complexity by 1 degree. Additionally, these columns are simply angular columns of the Pascal triangle. Finally, we can evaluate the polynomial equations that will generate each of these columns. Contrast this table to the one displayed previously. Like in the previous table, there are rich and meaningful relationships between each of these equations. However, when we started from the proper vantage, these relationships become more clear. To summarize, we solved for a general function signature in several ways. The first required us to polarize the Pascal triangle and resulted in a table of complex equations. This table, however, hinted to us of a better solution. Once we selected the proper method, we discovered we no longer needed to polarize the Pascal triangle, and also our table of equations was simplified. A web demo and JavaScript API of this video are available at math.d8data.io.